So this is going to be a video on the sixth chapter of the second section of geometry, which is more about proofs and stuff. Today we're going to make sure I do a mic check here. Okay. So today we're going to be doing stuff with angles rather than segments. So the last two things have been about segments and midpoints and segment addition postulate. Today we're just going to be applying that to angles. So again, it's not going to be really anything too terribly new. It's just going to be taking the segment stuff we did and applying it to angle measures. So first off, just like the segment addition, we have the angle addition postulate, and this is fundamentally the same thing. It says that you can take two angles and add them together to get a bigger angle. So right here in the picture here, they say, okay, I have this angle ABD, then I have this angle BC or CBD, and if I add them together, I can get the entire angle ABC. So this angle here plus this angle here is equal to the entire angle itself. So you can always add two angles to get the bigger angle, just like you can add two segments to get the bigger segment. Now, in this case here, these two angles have to be adjacent. So for example, I can't do this. Let's say I call this A, B, C, D, and E. So what I can't do is say that angle ABE plus angle CDE is the same as angle AC or AED. So I can't say that this angle here plus this angle here is the entire arc because I'm missing this middle part. Now I can add all three of these together and say that they are the entire arc, but when you add the angles together, you have to make sure that they're back to back essentially, or side to side, so that the actual arc is connected through all the angles that you're adding. But again, fundamentally, it's the same thing as segment addition. You take two smaller angles and add them to get the bigger angle. So again, let's just take a look at an example that they do here. So they have this picture off to the side. They have J, K, L. They number the angles as 1 and 2. That way they don't have to keep referring to it as J, K, whatever, and L, K, whatever. So they said that angle 1 plus angle 2 is equal to the entire arc, which is true. If you take angle 1 plus angle 2, you get the entire angle JKL, the entire swing there. That's the angle addition. And they say that angle 2 is 56 and JKL is 145. So they plug in those numbers to their respective spots. And then using algebra, they just solve it down to get that angle 1 has to be 89 degrees. And they use their reasonings over here. So they kind of do like a pseudo two-column proof. So this would be the first reasoning, second reasoning, which would be kind of like given, and then third and fourth to finish it out there. So it's kind of like a faux two-column proof there. But that's, again, very basic algebra problem involving angle addition. You can add these two angles to get the entire big angle that they're made out of. So let's try one on our own here. So find the measure of angle 3 if angle 1 is 23 degrees. So we'll put a little 23 here. Angle 1 is 23 degrees. And ABC, so A to B to C. So the entire thing is 131. 131. So, well, what do I know? Well, I know that if I take angle 1 plus angle 2 plus angle 3, which is this space right here, I can get the entire arc. So I'm going to start off with that. Angle 1 plus angle 2 plus angle 3 is equal to the entire arc ABC. And it says justify each step. So over here, we're going to put kind of our reasoning. So we'll do this in kind of a two-column proof way. Our reasoning is angle addition postulate, which says that I can take smaller angles, add them together to get the bigger angle. And this is angle 3, not a B. So then now I'm going to use the given to kind of, or I guess you could also say substitution, to kind of put in some numbers in here. So they say that angle 1 is 23 degrees. So I'm going to take this angle 1, put in a 23. They don't tell me what angle 2 is, but over here I see that there's a little right angle box. There's a right angle box there. So I know that angle 2 has to be 90. Angle 3 I don't know, so I'm just going to call that angle 3 is equal to, and they say ABC is 131, so I'll put 131 there. So then now if I said solve for angle 3, what you would probably do is you combine like terms. So it'd be 113 plus angle 3 is equal to 131. And that is just simplifying. I'll put SIMP for short. So, or you could say combining like terms, either one. Then you subtract 113 from both sides. And you get the angle 3. So you take 131 minus 113. Let's do that here real quick. 131 minus 113 ends up being 18. And so this was this part right here was subtraction property of equality. And that'd be your answer. So once again, the idea here is that you can take smaller angles, add them together to get a bigger angle. Just like you can take smaller segments, add them together to get a longer segment. Now, there are things that come off of this here. The supplement theorem and the complement theorem. So the supplement theorem says that if you have a linear pair, which remember is that Y shape, so linear pairs are angles that kind of form that sideways Y looking thing, this thing right here, or that make a full, I shouldn't say full half, but linear pairs make that half circle, right? Um, if they form a linear pair, then they're supplementary, which basically means that they add to 180. So if I see this in a problem, I can say that angle 1 plus angle 2 add to 180 because I know that they are a linear pair. And then the complement theorem is, again, kind of the same thing, just with 90 degrees. So if you see a little right angle box right here, right angle box, and you see that that's been split into two smaller pieces, angle 1 and angle 2, well, you know that if I take angle 1 plus angle 2, I'm going to get back to this right angle box or get back to, as they say, 90 degrees. So basically, if you have a linear pair, you can add them to 180. If you have a right angle box, you can add them back to 90. And again, the whole idea here is to get a sum that you can then substitute stuff in for to kind of prove a theorem. Okay? Just like we did that with segment addition. So let's take a look at one here. This is still algebra-ish, so we're going to still start with the algebra stuff. So it says angle 6 and angle 7 form a linear pair. Now we don't know that they're right angles, so they look like they'd be right angles here, but we don't know that for sure. We do know that they form a linear pair. If angle 6 is this and angle 7 is that, find what angle x is, find what angle 6 is, and find what angle 7 is, and then justify each step. So we're going to start by saying that if they're a linear pair, then I can say that angle 6 plus angle 7 is equal to 180. How do I justify that? Well, because of supplementary angle theorem. So this is the abbreviation for supplementary angle theorem, which is exactly what this said here. Or you can say supplement theorem, either one. But that says that if you have a linear pair, so if you have a linear pair, then you have supplementary angles. Then they add to 180. So that's why it's have here. They have a linear pair, so the if has been satisfied. Therefore, they're going to add to 180 because, again, it's a theorem. I can use that. And then what I'm going to do is use substitution now, right? So I'm going to plug in the values here. So 3x plus 32 for angle 6, 3x plus 32, plus 5x plus 12 for 7, 5x plus 12. And that's going to equal 180. Again, how would I justify this? Well, I would say substitution, because you're substituting in the actual values for the angles themselves. Or you can say given, because technically they did give you that information in the problem. And then we're just going to combine like terms. So here, that'd be 8x. Here, that would be 44 is equal to 180. So that is simplifying or combining like terms, whatever you want to say. Then what I would do is I would subtract 44. You get 8x is equal to, let's see here, 180 minus 44, making sure I don't mess up here. That would be 136. And then divided by 8, divided by 8. 136 divided by 8 would end up getting me 17. So I should probably justify these here. This was justified by subtraction, property of equality. And then this was justified by division, property of equality. I can divide the same thing to both sides. So this is what x is, and then I'm basically done with my proof part, because now that I know what x is, I can plug it in to find out what angle 6 and angle 7 are. So angle 6 would be 3 times x, or in this case 3 times 17 plus 32. And then angle 7 would be 5 times 17, 17 plus 32, or plus 12 rather. So if we find this out here, 3 times 17 plus 32 would give me 83. And then 5 times 17 plus 12 would end up giving me 97, I believe. 5 times 17 plus 12, yep, 97. So these would be my two answers for the individual angles. So once again, supplement and complement theorem is simply there so that you have a sum that you can then swap in values for and hopefully proceed to either prove or solve a problem. That's all it's there for. Come on. So there's extensions we have on this here. So we have congruent supplements and congruent complements theorem. And what these basically tell us is how to connect. They're kind of like transitive almost, actually. So let's do the supplements one. Supplement one says that if you have two angles that are supplementary to the same angle, then they have to be congruent to each other. So put an example here. If I say that angle 1 is supplementary to angle 2, which means that angle 1 plus angle 2 adds to 180, and if angle 3 is also supplementary to angle 2, that means angle 1 and angle 3 have to be equal to each other. Now, again, this intuitively should kind of jive here because let's say that if I add some numbers to these, so same scenario, let's say that this angle here was 50. Well, if this angle is supplementary to 50, that means it has to be 130 because 50 plus 130 is 180. Let me try to make that second one a bit nicer. So if this angle is supplementary to 50, it has to be 130. That way they add to 180. And if this angle is supplementary to 50, well, it also has to be 130. So these are going to be equal to each other. So it's kind of like a play on the transitive property. Two angles that are supplementary to a third same angle are equal to each other. And then complements is the same thing, just with complementary. So if angle 4 is complementary to angle 5, and angle 6 is also complementary to angle 5, then they have to be equal to each other. Again, complementary is just dealing with them adding to 90 rather than 180, but it's the same sort of process. So this would be kind of how it would be used in a proof. This is a more geometric proof here that we're getting to. So it says assume that 1 and 2 are supplementary, and assume that 2 and 3 are supplementary. Prove that 1 is congruent to 3. So this is actually proving the theorem we just talked about. This is actually why it works. So angle 1 and 2 and angle 2 and 3 are supplementary. That's our given. So 1 plus 2 is 180, and 3 plus 2 is also 180, which is what they say here. So angle 1 plus angle 2 is 180. Angle 2 plus angle 3 is 180. Why? Well, because they're supplementary. That's what it means for them to be supplementary, is that they add to 180. Well, if this is true, that means they're both equal to 180. Both of these sums are equal to 180. So you set each side equal to each other. This is just substitution. I'm taking this sum and swapping it in for the 180 up there. So I'm replacing something. I'm substituting a sum in for a number of equal value. Well, this is where we go on to that reflexive bit here. Angle 2 is the same as angle 2. Something is equal to itself. So angle 2 is equal to angle 2, and we call that reflexive. This is usually one that you can actually skip, a step you can actually skip sometimes. But like I said, it's good to kind of say it verbatim there just so people know that that's where you're going with. And then they jump down and say that angle 1 is equal to angle 3. So what they basically did is they went back to step 3 here, and they said, okay, I'm going to subtract angle 2 from both sides. So this would cancel, and I'd be left with angle 1 and angle 3. So that's where they get the subtraction property of equality, they should have said there. Subtraction property of equality for their answer there, is they just subtract angle 2 from both sides. And so then they end up with definition of congruence to make angle 1 congruent to angle 3. So this is an example of how to prove what we just taught. This is a proof of why we can use this theorem here, that if you have two things that are supplementary to the same angle, that means they're congruent to each other. Because notice here we didn't use any number other than 180 because that's what we use for supplementary, which is the goal for geometric proofs. Geometric proofs want as little numerical stuff as possible because they want to prove things in the general sense. Whoops. So let's try one on our own here. So we have that ABE and DBC are right angles. So ABE and DBC are right angles. So these two sort of big angles here are 90 degrees. We want to prove that ABD, so we want to prove that this angle here is congruent to EBC, which is this angle here. So we want to prove that those two angles are congruent, given that the overall angles are right angles. So let's start with our two columns here. I'm just going to do this here, ABE and DBC, whoops, DBC equal 90. and that is given because I'm given that they're right angles. And again, right angles means equal to 90. So ABE and DBC is equal to 90. That's my given. Now, if I notice here, those are big angles, so I can break them down into smaller angles, right? So I can say, my pen here, I can say that angle ABE is basically this angle plus this angle, right? That's what angle ABE is. This entire big angle here is ABD plus DBE. So I can say that angle ABE is equal to angle ABD, which is this angle right here, plus angle DBE, which is this angle right here. So angle ABD plus DBE is the entire angle ABE itself. And the same thing for the other one. So I can say, I didn't want to do that. Darn, well, that's unfortunate. Now I have to rewrite that all over again. So let me rewrite it here real quick. Fumble fingers today. And this is the and symbol in case you didn't know. So ABE and DBC equal 90 because of given. And I know that angle ABE is equal to angle ABD plus angle DBE. And I also know that DBC is made up of these two smaller angles. So I can say that angle DBC is equal to angle DBE, which is this angle right here, plus angle EBC, which is this angle right here. And this is by angle addition postulate, because I'm adding angles together. I'm adding these angles together to get their bigger counterpart. Okay? Now, if that's true, that means that this angle right, these two angles are basically adding to 90, right? Because I know that ABE and DBC equal 90. So I can swap these out by just saying 90 is equal to angle ABD plus angle DBE, and 90 is equal to angle DBE plus angle EBC. So this is just substitution, because I'm substituting in 90 degrees for its respective angle, which are these two right here, because again, I know that they're both right angles. Now, if that's true, and I know that these two angles add to 90 and these two angles add to 90, that means they're complements of each other, right? Because complementary angles are what adds 90. So I can say that angle ABD and angle DBE, also these two angles down here, DBE and EBC, are complementary, COMP. How do I know they're complementary? Well, that's by, again, definition of complementary angles. Complementary angles are angles that are defined to be adding to 90, and I just said right here that both these angles add to 90. How do I know they add to 90? Well, because they add to ABE. And then why is that true? Well, because ABE is equal to 90. So I just kind of follow that chain down there to eventually get them to equal 90. And if this is true, we'll notice here that we have this angle is complementary to DBE, and this angle is complementary to DBE. So what we end up with here in our last reason, which I'll put over here, is that angle ABD is congruent to angle EBC because of congruent. I'm going to write the symbol here because that's going to get way too small to write in there. So I know that they're congruent because of the theorem we just talked about, the congruent complements theorem, which says that if you have two angles that are complementary to the same angle, in this case DBE, then they have to be congruent to each other. That's what this theorem was back here, congruent complements theorem. Two angles that are complementary to the same angle are congruent to each other. So that's what we have here. Two angles, ABD and DBE, or EBC, that are complementary to the same angle DBE, therefore they have to be congruent to each other. So, again, I know this is kind of a long one, so stick with me here, just a little bit more to go. We can state, when we're stating reasonings, we can state them in full, or we can just state the theorem, axiom, or definition name. So remember, vertical angles are always equal, right? So this angle is always congruent to that angle because they're vertical. So you can either say as a reasoning, vertical angle theorem, or you can say that vertical angles are always congruent. So some people get hung up on what do I say as a reasoning. If you don't remember what the theorem's name is, because eventually we'll get to kind of have a lot of these theorems, if you can't remember what the theorem's name is, but you know what it says, you can just write down what it says instead. So the vertical angle theorem says that vertical angles are always congruent. So you can just write that down if you don't remember that's called vertical angle theorem. So here's an example of this case here. Prove that DB bisects ADC, then, or sorry, if DB bisects ADC, then angle 2 is congruent to angle 3. So I want to show that angle 2 is congruent to angle 3, given that there's a bisector right here. So then the DB bisects ADC. So ADC, so DB is this line right here. And that bisects ADC. So here's how they go about it. They say, okay, this is our given. Well, because the bisector, I know that these two halves are going to be equal. Angle 1 and angle 2 are going to match up because, again, they're both halves that's been bisected. So angle 1 is congruent to angle 2 because that's what a bisector does. Definition of angle bisector. Just like we say definition of midpoint. A midpoint cuts a segment in half. A bisector cuts an angle in half. So definition of angle bisector to get these two halves to be equal. And then it says angle 1 and angle 3 are vertical angles. And we can see that by the picture here. So if they're vertical angles, they say by definition of vertical angles, I would say given. So I wouldn't necessarily agree with this reasoning right here. I would have just said given, but to each his own. So therefore, if they're vertical angles, that means angle 3 has to be congruent to angle 1. Why? Well, because vertical angles are congruent, or you could have just said vertical angle theorem. Okay? So vertical angle theorem or vertical angles are congruent means the same thing, same reasoning. So we have 3 is congruent to 1, and we have 1 is congruent to 2. Well, again, we have a chain here. We have a link here. So we have angle 2 congruent to angle 1, which is congruent to angle 3. So remember, if we have a chain, we can always connect the ends of that chain by using the transitive property. So that's what they code through here. They say angle 3 is congruent to angle 2 because of the transitive property. I can connect the ends of the chain together, and then we flip it around to make it more like the proof statement. So the proof statement says 2 congruent to 3. Therefore, we can flip it around the congruency sign using the symmetric property and present it like they want it to be. So again, you have some leniency on how you state your reasoning, and if you memorize all the theorems and know all their names, it's great. But if you just want to say what the theorem says verbatim rather than actually writing out the name, that's fine too if you forget in a pinch there. So these are some more theorems that we are going to come into play later on. Again, you don't necessarily need to memorize the numbers, just memorize what it says, or at least get familiar with what it says. And again, a lot of these are intuitive, so it looks like a lot of information, but it's actually not that much. So for example, perpendicular lines form 4 right angles. Well, we kind of knew that already. If you have perpendicular lines, that means that you intersect at a right angle. And we know that they're going to make 4 of them because they intersect basically at 4 angles. 2 intersecting lines make 4 different angles. So if they're perpendicular, they have to be 4 right angles. All right angles are congruent. Well, again, it's kind of intuitive. If you have a right angle, that means you're equal to 90. And therefore, if you have 10 right angles, you have 10 angles that are equal to 90, which means that they're going to be congruent to each other because they're all equal to 90. So a lot of these sound like they're complex, but they're actually not. I'm not going to go through each one. You can obviously read it on your own if you want to. But these are just some theorems that we can come into play and use when doing proofs here. So again, if you have any questions on these, please let me know. And again, they give you a diagram and an example down here. But again, please let me know if you have any questions on these, and I can help explain it further. So that's it. So like I said, kind of a long one, I know. Again, we're starting to get a lot more theorems under our belt, a lot more tools we can use when proving stuff. And again, it's a process that will take time. So if you're still struggling with it a little bit, don't worry. We're going to take this as slow as we can. As always, make sure you email me if you have any questions. Otherwise, hopefully you enjoyed this video, and have a good day, night, or afternoon.